anticipating that you experienced that dull opening, you would appear in another universe. There is, at this point, a connection between quantum handling and faint openings. In this educational video, we investigate a fundamental and frightening discovery made by the James Webb Space Telescope. Inside a faint opening, as Bill Nye, the science guy, explains, a faint opening is a star so gigantic that even light can't escape from it due to its immense gravity. The confusion has resulted from dark secrets that have puzzled experts for a long time. However, thanks to remarkable technological advancements, we've seen something truly unbelievable. The incredibly huge dark opening consumes what is comparable to a single Earth every year. The first mesmerizing image of a faint opening in space is both amazing and tempting. Prepare yourself as we dive into the intricate details of this endless expanse and what it might imply for our comprehension of the universe. Formation of faint openings. Stars nearing the end of their lives, especially those significantly larger than the Sun, run out of fuel and start collapsing as gravity crushes them. Faint black holes and other openings are fascinating, but identifying the first one was a challenge. Despite the fact that Einstein's theory of relativity predicted their existence, unlike stars, faint openings emit no light of their own. Their size and rotation are the only measurable properties. The first visual proof of faint openings has only recently become available. While scientists suspected their presence for decades, the first Sagittarius X1 was encountered in 1964. However, it took more than 30 years for experts like Kip Thorne and Stephen Hawking to confirm whether Sagittarius X1 was, in fact, a hazy opening. Hawking, a prominent figure in black hole research, firmly believed in their existence, though conclusive evidence was lacking. Thorne and Hawking were almost certain in 1975 that Sagittarius X1 was a faint opening. By 1988, they were 95% certain. However, they waited until 1990 for solid confirmation when further observations provided sufficient evidence. The first discovery of Sagittarius X1 was made utilizing two spaceborne Geiger counters on a suborbital rocket. The signals detected pointed to a galaxy 7,200 light-years away, where a massive blue supergiant star orbited another enormous object emitting strong X-rays, consistent with the presence of a faint opening. Extensive research has since focused on Sagittarius X1, revealing that it is over 20 times the mass of the Sun, making it the largest stellar mass faint opening discovered without the use of gravitational waves. This discovery challenges long-standing theories regarding the formation of black holes and the mass loss experienced by stars over their lifetimes. Sagittarius X1 sets records not only for its immense mass but also for its extreme rotational speed, which is close to the speed of light. This contradicts previous models of black hole formation. Although definitive proof of faint openings has only recently emerged, they are now known to be dispersed throughout the universe. Even if scientists eventually unravel all the mysteries of Sagittarius X1, numerous other black holes still hold immense secrets. Gaia BH3. A newly discovered faint opening. Less than 2,000 light-years from Earth, researchers have found an inactive giant, Gaia BH3, the largest stellar mass faint opening in the Milky Way. It has a mass several times greater than that of the Sun. Despite being the second closest known faint opening to Earth, Gaia BH3 remained unnoticed until recently. Gaia BH3 was found accidentally when scientists from the European Space Agency, ESA, analyzed data from the Gaia mission, which creates 3D maps of the Milky Way. This dormant black hole is not consuming material from a companion star, making its discovery completely unexpected. Typically, tiny openings in the stellar mass category of the Milky Way have a mass of only a few times that of the Sun, with Sagittarius X1 holding the record at more than 20 times the Sun's mass. However, Gaia BH3 is even larger at 33 solar masses. Still, it is tiny in comparison to the supermassive faint openings, such as Sagittarius A*, SGR-A*, the central black hole of the Milky Way, which has a mass 4 million times that of the Sun. Gaia BH3 is the second smallest faint opening to Earth, behind only Gaia BH1, which is 1,500 light-years away and has a mass several times that of the Sun. These discoveries provide additional support for understanding how stellar mass black holes are formed. Role of heavy metals in faint opening formation. Faint openings form from the collapse of massive stars. Scientists believe that stars with lower heavy metal concentrations are the primary sources of these colossal stellar mass faint openings. These metal-poor stars, mainly composed of hydrogen and helium, have a slower mass loss rate, leaving more material available to form large faint openings when they die. JWST and a massive faint opening in the early universe. Utilizing the James Webb Space Telescope, JWST, experts have discovered an exceptionally massive red-tinged black hole from the early universe. As the universe expanded, this black hole took on a reddish hue, appearing 700 million years after the Big Bang. The light reaching us is redshifted, suggesting a thick layer of gas and dust surrounds the black hole. Astronomers Lucas P. Fennell and Avi Ben from the Bennett School of Cosmology used JWST data to determine the black hole's mass, over 10 billion times the mass of the Sun. This discovery is remarkable because it demonstrates that early supermassive faint openings were consuming surrounding gas and dust at an unprecedented rate. Located 12.9 billion light-years from Earth, this quasar was first identified by its red coloration. Quasars form when enormous amounts of material surround extremely large and faint openings, producing a glowing gas disk and dust. The intense gravity disturbs this substance, causing extreme heat and immense brightness. Quasars are so luminous that they outshine all the stars in their surrounding galaxies. JWST identified this massive faint opening as a tiny point due to the enormous radiation it was emitting. Initially mistaken for a distant developing star or galaxy, further color analysis confirmed its nature. It was actually an early universe. The role of supermassive black holes in this discovery was made possible by gravitational lensing, a phenomenon Einstein predicted in 1915. According to Einstein's general theory of relativity, massive objects bend the fabric of spacetime, creating a natural magnification effect. This enables astronomers to observe distant objects that would otherwise be invisible. Gravity plays a crucial role. The larger the object, the more it distorts spacetime, affecting the light emitted by stars as it passes near massive objects. This phenomenon, known as gravitational lensing, allows us to see far-off objects that would otherwise be undetectable. The JWST utilized this effect, aided by a galaxy cluster called SMX J7233-7327, to amplify the brightness of distant galaxies and uncover new data about a red quasar. This discovery adds to the growing body of evidence that the early universe was populated with unusually large black holes, some millions or even billions of times more massive than the Sun. Since similar anomalies have been observed in other early universe black holes, this finding sheds light on the coevolution of black holes and their host galaxies. However, the classic chicken or egg question remains on a grand cosmic scale. Did the universe or black holes come first? How large were the first black holes, and how did they grow? Experts may have uncovered evidence that microquasars, black holes consuming companion stars, are colossal particle accelerators producing unexplained high-energy cosmic radiation that reaches Earth. These giant black holes consume material from neighboring massive stars in binary systems. Some of this stellar matter is ejected as relativistic jets traveling at incredible speeds. Microquasars are smaller versions of quasars, both powered by supermassive black holes feeding on surrounding matter. In 1912, high-energy particles were observed hitting Earth with energies reaching 10^2 electron volts, far greater than those produced by the Large Hadron Collider, the world's most powerful atom smasher. Theoretical models suggest that supermassive black holes and microquasars are the universe's most extreme particle accelerators. However, direct evidence of microquasars propelling particles to such high energies has only recently been verified. Using high-energy observations, the HESS, High-Energy Stereoscopic System, detected exceptionally high-energy gamma rays from the jets of the Milky Way's most powerful microquasar. This established a link between cosmic rays and microquasars, such as SS433. SS433 generates high-energy gamma rays through its jets, which interact with surrounding matter, producing shock fronts that accelerate electrons to incredible speeds. These interactions result in gamma-ray emissions. CES 433, the first microquasar ever discovered, is located at the center of the W50 supernova remnant, often referred to as the Manatee Nebula. CES 433 has been extensively studied. The system consists of a black hole and a massive companion star, approximately 10 to 20 times the Sun's mass, orbiting each other every 13 Earth days. The black hole's intense gravity siphons material from the companion star, forming an accretion disk. Some of this material is funneled into jets that travel at 26% of the speed of light, creating a spiral pattern that gives W50 its distinctive shape. Over time, the jets fade and reappear in a predictable cycle. CES 433 is one of the most fascinating objects for studying microquasars and cosmic particle acceleration. Despite being the first identified microquasar, many questions remain about how black holes accelerate particles to extreme energies and their broader impact on the universe. Scientists employ various observational methods, including indirect measurements, to study these enigmatic objects. Black holes can be detected through their interactions with surrounding stars and matter, as evidenced by dramatic increases in X-ray emissions when material falls into their gravitational grip. This process is crucial for understanding black holes and their influence on the universe. The recent discovery of the most distant known black hole, located 13.1 billion light-years away, has deepened our understanding of these cosmic giants. The JWST's capabilities enabled the detection of this exceptionally large black hole, which formed less than 1 billion years after the Big Bang. This challenges existing theories of black hole formation and galaxy evolution. Evidence suggests that early black holes played a significant role in shaping the structure of the universe. Beyond forming galaxies, black holes are linked to powerful cosmic phenomena known as active galactic nuclei, AGN. AGNs are characterized by intense emissions from regions surrounding supermassive black holes at the centers of galaxies. These emissions occur as material from the accretion disk is heated to extreme temperatures while spiraling inward, releasing X-rays and other radiation. Studying AGNs provides insights into black hole feeding behavior and their effects on host galaxies. Research indicates that AGNs significantly influence galaxy evolution by regulating star formation and distributing heavy elements across galaxies. Recent advances in gravitational wave cosmology have revolutionized our understanding of black holes. Observatories such as LIGO, Laser Interferometer Gravitational Wave Observatory, and Virgo have detected gravitational waves from merging black holes, opening new frontiers in astrophysics. By analyzing these ripples in spacetime, researchers can infer key black hole properties, including their masses, spins, and even their origins. The discovery of intermediate mass black holes has bridged the gap between stellar mass and supermassive black holes, offering new insights into their growth and evolution over cosmic time. Recent studies suggest that black holes impact their host galaxies far beyond their immediate surroundings. Relativistic jets and powerful outflows from AGNs regulate star formation by heating and dispersing surrounding gas, preventing it from collapsing into new stars. This process, known as black hole feedback, is believed to play a crucial role in shaping the large-scale structure of the universe. Beyond their impact on galaxy formation, black holes are essential to understanding the fundamental nature of space. The study of black hole event horizons, regions beyond which nothing, not even light, can escape, has led to groundbreaking insights into quantum information and gravity. Stephen Hawking's work on Hawking radiation suggests that black holes gradually lose mass over time and eventually evaporate. However, the fate of the information contained within them remains one of physics' greatest unsolved mysteries. With the advent of next-generation observatories such as the Einstein Telescope and the LISA, Laser Interferometer Space Antenna, researchers hope to explore black holes in even greater detail. These future missions will enable astronomers to detect gravitational waves from black hole mergers at unprecedented distances, shedding light on the earliest epochs of the universe. Multi-messenger astronomy, which combines gravitational wave detections with X-ray and radio observations, has opened a new window into black hole research. By studying signals at different wavelengths, Researchers can reconstruct the dynamic processes occurring near black holes, from the infall of matter to the launching of powerful jets. Despite remarkable advancements in black hole astrophysics, many fundamental questions remain. How did black holes form in the early universe? What role did the first black holes play in cosmic evolution? Could black holes themselves be gateways to new dimensions or remnants of past universes? As our understanding of black holes deepens, so does our appreciation of their profound influence on the cosmos. From shaping galaxies to accelerating particles to unimaginable energies, these enigmatic objects remain at the forefront of modern astrophysics. With new discoveries on the horizon, the study of black holes promises to unlock even more secrets about the fundamental nature of the universe itself.